Let's tell our listeners just a little bit about this man named David Scott, who is now a lieutenant colonel in the United States Air Force, assigned to NASA as an astronaut, command module pilot of Apollo 9. Where were you born, and what's your background? Where'd you go to school, and what were you interested in back then as a little guy?
Well, I was born in San Antonio, Texas, 1932 on June the 6th, and my father was in the Air Force.
So you moved around some, I bet.
Yes, I did. I spent time in Texas and Illinois and California, and we spent an overseas tour in the Philippines. And I traveled quite a bit, and I enjoyed every minute of it.
And you lived in Washington for a time?
Yes, I did. Washington, D.C. I went to high school there, as a matter of fact.
Was your father a pilot?
Yes, he was a pilot, and from my youngest days, I can remember airplanes and wanting to fly airplanes, and I guess that's what led me down the road.
Then you went to West Point, didn't you?
That's right.
And when did you graduate there?
Graduated in 1954, and then I went into the Air Force.
What were you flying there at first?
Well, I went through primary and basic flying training in single-engine jet, as they called it at the time, and then I went to gunnery school and went into fighters, and subsequently was stationed in Holland with an American squadron attached to the Dutch Air Force flying F-100s, and I spent 4 years there. I guess that was the bulk of my fighter pilot career. I had always also had a desire to be a test pilot, and I decided I'd try to get in the test pilot school at Edwards Air Force Base, and I figured the best course of action would be a little more education, particularly in this day and age, to better understand how the machines we fly work. So I applied through the Air Force to go to MIT, and was fortunate enough to be selected, and I took a course in aeronautics and astronautics.
Were you and Rusty Schweikert there about the same time, perchance?
Yes, but we didn't know each other. I guess we were there, we overlapped something like maybe 6 months, but it's a big school, and we never really had a chance to meet.
Then how did you put this aeronautics and astronautics new knowledge to work?
Well, I did subsequently get into the test pilot school, and I got to apply the aeronautics background, and after that I was accepted to the Aerospace Research Pilot School, which is a space-oriented school the Air Force has, where I got to apply the astronautics background, and from there I came here to NASA.
And when did you come into the astronaut program?
I guess we arrived in January of '63.
Tell us a little about the early docking with the LEM and withdrawal from the S-4B rocket.
Well, I guess the first major function we have in flight is to extract the lunar module from the S-4B third stage of the Saturn V. And to do this, we perform a maneuver called transposition and docking, which is nothing more than a turnaround maneuver and a docking of the command and service modules with the LEM. And the LEM is attached to the S-4B. After the docking, it's necessary to pressurize the lunar module and attach a couple of electrical umbilicals in order to make electrical contact with the release mechanism, enabling us to extract the LEM from the S-4B. Well, the docking maneuver is very similar in technique to the maneuvers we performed in Gemini, although the mechanism is quite different. And the visual aids we use are quite different because, unlike Gemini, we cannot see the actual point of contact at the docking interface, as we call it. We use a probe and drogue method to attach the vehicles together.
You have a sighting device both in your window and then a mechanical device on the lunar module that you can come into, though, that will help align you, don't you?
That's right. We have what we call a standoff cross and an optical alignment sight. And the sight is in the command module and the cross is on the LEM. And you align the two, which ensures that the probe and drogue are aligned. And then you close, make contact, and there are some what we call capture latches, which are small hooks in the end of the drogue, which are in the end of the probe, which initially join the two vehicles together in a as we call a soft dock position, which provides us with somewhat of a spring damper system between the large S-4B LEM combination and the CSM. And after we have done this soft docking and stabilized the motions between the two vehicles, then we retract the probe. We pull the two vehicles together mechanically using the probe to a hard dock position, as we call it, whereby the two vehicles are attached mechanically by 12 docking latches around a hard ring.
There's been a lot of interest in this docking mechanism by many of us. Is this dangerous at all, do you think?
Well, it's not dangerous, but it's a very complicated piece of machinery, and there are many, many moving parts, and a lot of things have to work just exactly right in order to successfully complete the link-up.
Now, does anyone inspect this connection?
Yes, as soon as we get docked, before we extract the limb from the S4B, it's necessary to look at the connection in the docking tunnel and make sure that we have, in fact, made a successful hard connection between the two vehicles. And this requires removing the hatch, the inside hatch from the tunnel in the command module, and going up and inspecting the docking latches and the probe and drogue.
Mm-hmm. And then you have several days in which you stay docked before the long rendezvous exercise.
That's correct. We stay docked. The second day we perform a number of SPS maneuvers, and the third day we do the limb systems checkout, and the fourth day the EVA, and all those days we remain in a hard dock configuration.
Dave, what is the purpose of this long series of service propulsion system burns on the first and second days of the mission?
Well, I guess it has two purposes, really. The first is to demonstrate that we can perform a lunar orbit insertion maneuver with the lunar module attached to the front of the command module. As you remember, on Apollo 8, we did the lunar insertion into lunar orbit with the command and service modules, and that demonstrated the guidance technique of the one vehicle. Now we have to demonstrate the guidance technique of the two vehicles joined in order to put the combination in the lunar orbit. And we'll simulate that particular maneuver in Earth orbit. Another purpose is to demonstrate the structural integrity of the two vehicles. In other words, how well does this system hold together, you might say, and how stable is the guidance system. And we want to ensure that we have a stable system, yet we also want a tight loop, if you will, to have to make the guidance as best possible. We evaluate the stability margins of the guidance system by actually exciting the bending modes of the combination in an exercise we call a stroker. We actually move during the burn while the service propulsion system is actually ignited. We force the engine to move up and down, the engine bell, to actually excite the bending modes between the two vehicles, not to try and break them apart, because we wouldn't do it if we thought they'd break apart, but to see how stable the guidance system is, how much it can compensate for in the bending,
mm-hmm.
and still keep a straight course.
How much weight is there in the combined vehicle mass?
It's 96,000 pounds.
96,000 pounds. So that's reason enough for considerable testing and evaluation.
Yes, and it's a long, narrow beam with a, as you might say, a fragile joint in the middle. It's not really fragile, but that's the point at which we get the most structural deformation.
Dave, during the extravehicular activity of Rusty Schweikert, you will remain in the command module, right? What will you be doing?
Well, my job is to set the command module up to receive Rusty, or anybody, as a matter of fact. We're demonstrating the EVA transfer. So my job will be to make sure the command module is ready to receive the two crew members from the lunar module in the event we have to go outside the vehicles to transfer from the lunar module to the command module. And during our particular exercise, I'll set the command module up as far as the interior configuration, which means removing the center couch and stowing it. And I'll depressurize the command module and open the hatch and take a peek out to make sure Rusty's on his way.
Dave, your busiest day, I'm sure, is going to be the day on which the lunar module separates from the command and service module and goes off on this rendezvous exercise. Now, you will be there alone in the one craft which can bring all three astronauts back to Earth. That's quite a responsibility. What will you be doing?
Well, my primary function is to back up each of the lunar module maneuvers, and by that I mean be prepared to execute what we call a mirror image maneuver to keep the two vehicles in the same relative position at all times. And in order to do this, it's necessary that I navigate through the rendezvous just as the lunar module does. And we have somewhat of a new concept. In order to keep everybody appraised of where we are and keep a relatively nominal trajectory at all times, why both vehicles are active. Both vehicles navigate and both vehicles prepare to do the maneuver. The difference being only one of them pushes a button and lights an engine. And which one is sort of a real-time decision. The lunar module always does unless it has a problem and cannot. And in that case, the command module does, and it performs a maneuver 1 minute late.
I've heard the phrase mirror image maneuvers in reference to what you'll be doing.
Yes, that means that because of the relative motion of the two vehicles, if the lunar module makes a maneuver, it goes in a prescribed manner relative to the command module. Now, if we want to keep that same relative motion between the two vehicles, and the lunar module cannot make the maneuver at the prescribed time, then the command module can, with a certain known adjustment, make a mirror image maneuver, just a backwards maneuver from the limb.
To stay with it.
To stay with it and keep the same relative motion.
Mm-hmm.
And in this way, we always know where one vehicle is relative to the other, which is the essential part of